Yeah, good morning dear viewers. This is Dr. Gunamani Jana, and in this video lecture we are going to cover regarding the NAND and NOR implementations. This is one of the university questions and it is a frequently asked questions, and so many students they asked about go for this NAND and NOR implementations. In this video coverage today we will be going for this NAND and NOR implementations, right? So now what is this NAND and NOR implementations and how do we do that one, that I am going to discuss here, right? We see this diagram, how using this NAND gate we can represent everything, or how using this NOR gate we can represent everything. For this what you need to do, see, any logic function can be implemented using a NAND gate. That is the main thing you remember. To do that one, what you need to do? To achieve this, first the logic function has to be written in a sum of product form. You know the sum of product and product of sum. Okay? Whatever the logic functions are there, it must be written in the sum of product form. And once the logic function is converted to the sum of form, then it is very easy to implement using the NAND gate. In other words, any logic circuit with AND gates in first level and OR gate in second level can be converted to a NAND gate circuit. Now let us take an example. Suppose a logic function f is equal to written as w into x into y plus x into y into z plus y into z into w. So this is the logic function it is written. Suppose the output is coming like this. Okay, the above circuit is the above expression I have to convert to a AND gate circuit. So w x y, you can see here w into x into y. This is the AND gate I am using. Then x y z, all the three input I am putting it AND gate, and y z w, this also I am putting AND gate, and because these are all connected, so then I am connecting through an OR gate. Okay, so this is the f, output f. So this is the first level. What is that? Is the AND level. Second one is the OR level. So this is the things remember. Now what I want to do, as per this the stage number 1. First the logic function was written, we converted into the SOP sum of product, then we converted them to the logic circuit here like that, first stage using this AND gate and OR gate. Then what we did, now we have to make the bubbles. That means initially whatever things are there, because I have to convert this to NAND gate, so then this AND gate just I bubble it. That means I want to make it NAND gate. So the first one is converted to NAND 1, second one is converted to NAND 1, third one is converted to NAND 1. So if bubbles are introduced at AND gate output, if AND gate output bubbles are used, then you have to put the same thing at the OR gate input. Are you following me? So if a bubble is here, the same thing is introduced at the bubble gate, because negative of negative it becomes positive. So that's why, so up to this it is okay. Is it clear what I am telling you? That suppose for this first AND gate I put a bubble here, then before the entry of the input to the OR gate I put another bubble here. Same thing I have done for this one here, same thing I have done for this one, same thing also I have done for this one. Is it clear up to this? Now what you do, the first stage AND level converted to NAND level, it is okay. The second input, what you see, the bubble input of the OR gate, it is same as if you put that, you convert that OR gate to AND gate and put the bubble at the end. You just make a truth table and you see the output will be same. Okay, so this is the thing how he implemented the AND and OR gate into a NAND gate. This is the same as that one. Okay, how realizations or how it takes place. The realization of logic gate using the NAND gate. First let us go for the realizations. Now we are going for implementing an inverter using NAND gate. What is the inverter? Inverter means, see, invert of something or invert of something, that is the thing. Okay, suppose I take two inputs x and x. Here same x is given as input here and given as, and inverse of that one. Okay, x into x becomes x, that is the idempotent role. So x into x becomes equivalent to inverse of x. Okay, so if the same thing I am using, the function will be f is equal to x inverse or x bar, whatever you say. This is the NOT gate, okay, or the inverter using the NAND gate. I am using the same NAND gate and giving one input, I am converting it into an inverter or converting it to NOT gate. Clear? The implement of AND using a NAND gate. So first I implemented a NOT gate using the NAND gate. Now I am going to implement an AND gate using this NAND gate. What is the equivalent of that one? See, now see the input. So invert of or transpose of xy into transpose of xy. Okay, how you do all the things? See, see, what is the output of that one? This is xy, x into y, and this is transpose of xy. The same transpose of xy is given the input here, and the same is given input here. That means transpose of xy into transpose of xy and its transpose or inverse. How to find that one? See, using the same idempotent rule. So if xy is equal to a, so transpose of a and again its transpose, it will become a. Transpose of a, it becomes a. A is equal to xy, so it becomes xy. Okay. The first one is the idempotent rule. Second one is the involution rule. You know all the things. Okay. That is transposition of transposer of any number. It is equal to the same number. So for example, I take a. 2 times I make the transpose. Transpose of a again and its transpose, it becomes a. So that's why our initially xy was a. Its transpose, it becomes xy. So the same thing it is done here. Okay. Now what I have done here, using the NAND gate, I implemented AND gate. You get it now? Then implementing OR using NAND gate. How do I implement the OR gate using the thing? Okay. Implementing OR using the NAND, just I put it here. Now see here what I am writing, just to check it here. What is the input I am writing? Here input I am giving x into x transpose, y into y transpose. Okay, x into x transpose, y into y transpose, and its transpose. It should be equivalent to x plus y. If it is x plus y, what is x plus y? X plus y is a OR gate. Are you following me? Here input was given x and y, and finally the output is x plus y. What is x plus y? X plus y is a OR gate. That means I am using NAND gate to find the OR gate. Here what are the input? Here input was x into y. Input was x and y. Finally what is the output? Output is equal to xy. Xy is the AND gate. Okay. So using NAND gate, you try to understand what I am telling you. The first case, input was x and output was x dash. So this is a NOT gate or invert gate. Here the input were x and y, output is equal to x into y. It is a AND gate using the NAND gate. Here the input are x and y and output is equal to x plus y. So this is a OR gate implementations, right? Similarly, you understand what I am telling that? Then this is the transpose of a, so x into x, it is x, you know, this is the idempotent rule, and y into y, it becomes y. That means first is transpose of x into transpose of y and its transpose. Okay. Then transpose of a into b, that is transpose of a plus transpose of b. That means x transpose, again transpose x double transpose plus y double transpose. Double transpose of x, it is equal to x itself. Double transpose of y, it is equal to y itself. You get it? So this is the using the De Morgan law. What is the De Morgan law? A into b, transpose of a into b is equal to transpose of a plus transpose of b. You must remember this law and you have to involve. Then what is the involutions? I have given it here. Now implementing NOR gate using NAND gate. I am going to implement the I am using a NAND gate to implementing the NOR gate using NAND gate. Okay. Say what is a NOR gate? See, this is a NOR gate. X plus y, then its inverse, it is a NOR gate. F is equal to x plus y transpose of that one, right? Then how do I do it using a NAND gate? How do we do using a NAND gate? So what I have done, see, here I have given, see here, transpose of x. Can you see here? Transpose of x. It is transpose of x into transpose of y. Can you see it here? Transpose of x into transpose of y. And its inverse, suppose I put it here. So using this idempotent rule, it becomes x double bar, y double bar. This is a De Morgan law. So it is equivalent to x plus y. That is the involution. Okay. That is the involution. Now what if I go for the inverse of that one? That is equivalent to x plus y is the idempotent. So this is the realizations or implementation of NOR gate using the NAND gate. Next I am going what is the realizations of logic function using the NOR gate. Let us see what is happening. Say what we do. Say suppose initially it is given, you see this diagram. See this diagram. From this diagram you can understand. Okay. Initially what is given? It is given x plus y. Can you see here? X plus y. This is y plus z. OR gate I am using, and this is AND gate using. So f is equal to x plus y into y plus z. Initially it is given. So normally we are getting OR gate and AND gate. But what I am doing, I am going to implement using this NOR gate. Okay, how do I do all the things? So first is what I do, I make the bubbling of this output of this OR gate here, and here, and the input of this AND gate also I make it bubbling. So I make bubble here, I make bubble here, bubble here, bubble here, right? So up to this it is okay, and this bubbling of the input of this AND gate is equivalent to the bubbling at the output of the OR gate. So you get it now. Now the same circuit is converted to this one. Same circuit is converted to this one. How it is done? Let us see. Now see, suppose I am implementing an inverter. NOR, using this NOR gate I want to make it inverter. Okay. How it is done? Let's see. What is my input? Input is x. What is the inverter? Output should come x bar or transpose of x. How it is done? Here same x is provided as input x and x, and I am going for a transpose of that one. That means it is equivalent to x plus x transpose. So x plus x. What is x plus x? It is x. It is independent rule, you know. X plus x, 1 plus 1, it is 1. 0 plus 0, it is 0. You get it now. So x can be binary value, you know. So x plus 1 is equal to x. Then transpose of x is equal to transpose of x. I get it there. So here x to input I have given, and this is the OR gate x plus x, and the transpose of that one which is equivalent to that one. So that means using a NOR gate I can implement the inverter. Similarly, how to implement AND using a NOR gate? How to implement using a NAND? That means you use some NOR gate, and finally the output should come some AND. Okay. Here what is the input I am providing? Input I am providing x and y. What is the output? Finally it is coming x into y. That means it is a AND gate. That means I implemented the AND gate using a NOR gate. Okay. So in the first NOR gate, so x plus x, invert of that one, just I am putting it here, then plus y, invert of that one, and finally I am going for invert of that thing because another invert is there. So now invert of x plus x and invert of y plus y. What is the meaning of that one? So it becomes x plus x. What is that one? That is again x. Then it becomes transpose of x. I am writing transpose of x. Y plus y. That is again y. That becomes transpose. This is the idempotent rule. Okay. Then what I am writing that? Then x dash plus y dash, which is equal to x double dash y double dash, the De Morgan law. Okay, using a De Morgan law. So then what is the meaning of that one? Double transpose of x become x, and double transpose of y becomes y. You get it now? Initially I am giving the input x and y. Finally output I am giving x and y. That means AND gate is implemented using the NOR gate. Okay. Then I am implementing OR gate using a NOR gate. Okay. So what is the things? I have to give the input x, y. Finally I should get x plus y. This is the implementation of these things. Okay. Then the finally you will be going for implementing NAND gate using the NOR gate. So because this was little complicated, because so many students requested to start it first, because unless you understand all the concept, it was not that easy to understand. I think at this stage also 50 to 60% people will understand who little focus. The same material I have already shared. I have given you 2 years question paper. I have shared with you the model question paper. I have shared with you unit wise all the things what I implemented here. I hope all the things will be useful for you. Just only thing is that only 5 to 10 hours just to see all the things. It is enough to get more than 70% marks and clear the subjects 100%. Just remaining rest on you. So now we are going for the implementing the OR using this NOR gate. What is the meaning of that one? Here is x plus y and the transpose of that one. Same thing is repeated here. This is x plus y transpose, this is x plus y transpose. Again I am going for that one. That means x plus y transpose plus x plus y transpose and its whole transpose. Okay. Then what is the meaning of this one? See, this is the same as if transpose of x plus y and transpose of x plus y is same as transpose of x plus y. This is the idempotent rule. You get it now? Are you getting me? So it is just like a into b whole bar, that is a bar plus b bar, like that. Okay. So now this becomes equivalent to x plus y transpose of and transpose of x plus y. This is the idempotent rule. Now transpose of transpose, it becomes again x plus y. That means OR gate is implemented using the NOR gate because the inputs are x1 and final output are xy. Similarly, I am going to implement the NAND gate using the NOR gate. Right. So now you see, I want to implement the NAND gate using the NOR gate. Right. So what are the NOR gate? So I am giving x plus y transpose and x plus y transpose and whole transpose. See, what is the meaning of that one? This is x plus x transpose, this is y plus y transpose. Okay, x plus x transpose, this is y plus y transpose, and transpose of that one, what it becomes? Are you getting me? So okay, so then same thing is repeated here and here, and I am putting another NOR gate to find f is equal to x into y. Right. So you see here the input is provided transpose of x plus y plus transpose of xy whole transpose, which is same as transpose of x plus y, which is same as x plus y, and same thing is represented as. So this is the things we have implemented. The primary objective of all simplification procedure is to obtain an expression that has the minimum number of terms, and obtaining an expressions with a minimum number of literals is usually secondary objectives if there is more than one possible solutions with the same number of terms, and the one having the minimum number of literals is the choice, because we want to minimize the terms. And there are several methods for simplification of Boolean logic expression. The process is usually called the logic minimizations, and the goal is to form a result. Okay, so using the kernel map and all things we are doing. So this is, I don't think it is necessary for this chapter. We delete this thing. So up to this we have successfully implemented all the things. This material I am sharing with you. Please go through that one, and this video is also useful to all of you. See it again and again, pause it, and write down notes. Thank you for watching this video. Take care of yourself. Goodbye.